Welcome back to ECE 442-542. This session is a review for unit number 4, which is dealing with discrete equivalence, and maybe this title is misleading. Maybe what we should say, or have been saying, is discrete approximations. We're really trying to approximate analog or continuous time transfer functions with discrete time or discrete transfer function representations or realizations. In this session, we'll quickly review the process for the quizzes, and Unit 4 really is concerned with two different scenarios. Scenario number 1 deals with numerical integration techniques and pole zero mapping, and that's really where you're taking this controller or filter into its discrete equivalent or discrete approximation. And scenario number 2, and you might look at the very beginning or the very first lecture in this unit to review this summary or the overview. Scenario number 2 is where we actually have a zero order hold and a plant. Let me call that plant G of S. And an A to D. And we now take all of those, we incorporate the dynamic behavior of the zero order hold and the plant itself to produce a zero order hold equivalent, which is then called capital G of Z. In this semester, we've actually started with scenario number 2, which was dealing with zero order hold equivalents. You could do those either if your plant was represented as a transfer function or in the transform domain, or if you started with a state space representation. And the state space representation is then using notation-wise, the system matrix is A, the input matrix is B, the output matrix is C, and the direct feed-through matrix is D. For A, B, C, and D, you obtain these different types of discrete equivalents. One is exact, where the system matrix in discrete time is e to the AT. The input matrix is gamma, which is this integral of e to the A mu with the input matrix in the continuous time case B. The output matrix is the same in both the discrete and continuous representations, and the direct feed-through matrix is also the same. You could also numerically approximate phi. The exact is where you could even leave it as a function of the sample period capital T. The numerical approximation is probably what you would do in practice, and instead of doing this infinite series expansion where we're now raising A to higher and higher powers, you can show that that's equivalent when you cut this off at a fixed power. Let's say we went out to A to the 4th. That would be the same as this nested set of expressions where we now have, we start with the inner set, I plus AT over 4, then we pre-multiply that by AT over 3, add the identity matrix, and then from that combination, scale that by AT over 2, and finally add the identity matrix to that, and that gives us our psi matrix. Once we have psi, we can plug it in to obtain phi, and we can also plug it in to obtain gamma. That's scenario number 2, and you have either working in the transfer function setting or in the state space setting. Scenario number 1 deals with either numerical integration or pole zero mapping strategies. In numerical integration, you could do that in the transform setting, and we have a substitution table for that, or you could do it in the state space setting, and there was a table in homework number 4, problem number 5, that summarized those relationships, and those are true for, remember, we are now trying to do this numerical integration, and now maybe we want to figure out how do we approximate this last little add-on piece. Do we do it by looking forward? Do we do it by looking backward? Or do we do it by a bilinear or trapezoidal, where we use the previous y value with the present y value, and now we have this trapezoidal area that approximates the last differential area underneath this curve x, which we would then call the area under that curve would be y. We can do that then for those 3 different strategies. We also talked about pole zero mapping, and with pole zero mapping you need to worry about the zeros at infinity, both in the analog transfer function and the discrete transfer function, and how that needs to be interpreted. And we also need to worry about matching gains. Depending on what you start with in terms of a transfer function, you may want to match the gains at low frequency or DC. You may want to match the gains at infinity or at high frequency or some intermediate frequency. And I've now stated this relationship between S domain and Z domain for those 3 different scenarios: low frequency, high frequency, and intermediate frequency. In all of this discussion, you may have to pick a sample period, and that's going to be associated with the fastest pole in your analog system, or if somebody is going to be controlling that system, you may want to use the closed loop bandwidth. Once you have that, that's what we're now calling this omega sub f, the fastest frequency. And that's now omega sub s is 30 times that, where omega sub s is also 2 pi f sub s, or that's now 2 pi over capital T. This you can now set equal to 30 omega sub f and solve for t to find your sample period that you want to use in making this continuous to discrete approximation. The process for Unit 4, it's open note and open book. It will be a multiple choice. You can obviously be ready with both Laplace transform tables. You need to have access to those. You'll want a calculator or something to write with, but don't be talking with anyone in person or remotely. Don't be doing any computer searching. You're on your best behavior. The honesty conduct that we've talked about, no cell phone usage, and don't share your work or answers with anyone before, during, or after the quiz. The topics are homework number 4. Homework 4 dealt with zero-order hold equivalents in both state space and transform expressions. You need to be able to do numerical integration strategies, forward, backward, trapezoidal. Trapezoidal being called many different things, either Tustin or bilinear, and pole zero mapping. And for more practice, you should be able to use the old practice exam number 2s and find the appropriate problems dealing with Unit 4 material. One way to try to keep all of this straight is to think about a square of zero-order hold equivalents that connect time domain and frequency domain and continuous time and discrete time. In the time domain setting, we have this script S sub c, the A, B, C, D, if you now applied a zero-order hold to the input of that system and sampled, you would obtain this discrete time domain state space representation. Likewise, you could immediately go into the transform domain, or the finding a transfer function for that system by using this expression C Si minus A inverse B plus D. That's just Laplace transforming that state space representation and finding the transfer function between the input U and the output Y. Once you have that G of S, you could use the strategies in lectures 4.1 and 4.2 with the zero-order hold equivalent, divide that G of S by S, find the Z transform of that, and then scale that Z transform expression, which could consist of multiple terms, by this factor 1 minus Z to the minus 1. That gives you a capital G of Z. You could also obtain a capital G of Z if you went the other way. If you went horizontally with this discrete equivalent in the state space setting, and then Z transform the state space representation and find then your capital G of Z in a transform setting as this C times the quantity Zi minus phi inverse times gamma plus D. The zero-order hold equivalent, where this horizontal action is described in lecture 4.3, where we're holding the input constant in between samples. That's the zero-order hold characteristic. Then the phi matrix, the system matrix in the discrete time setting, is E, a matrix exponential, A to the capital T. T is a scalar, and if you wanted to obtain that phi matrix by hand, you could then find that by first computing this matrix symbolically containing S, this matrix Si minus A inverse, and then inverse Laplace transforming each of the elements in that matrix. That would then be a matrix that's a function of time t, little t. You could replace that with the sample period capital T to obtain the system matrix capital Phi for the discrete time system. The input matrix needs that matrix exponential multiplied by the continuous time input matrix capital B and integrate the left remaining terms in that matrix product e to the a mu times b. You integrate that over one sample period from 0 to t, and that produces gamma, which is your input matrix for the discrete time setting. If we were in scenario number 1, then we have these numerical integration discrete equivalents or discrete approximations, and depending on what kind of numerical integration strategy, if you go forward from the previous time, if you go backward from the current time, or if you combine those with a straight line, you end up with the appropriate Z transform expression that is used to substitute in for S in your original transfer function expression. Bilinear, you could think of that, or one way to think of that is this is a quotient of two linear expressions. If you wanted to think about performing this discrete equivalent using numerical integration in a state space setting, then you can use either the forward, backward, or trapezoidal to find the system matrix capital Phi, the input matrix gamma, the output matrix H, and the direct feed-through matrix J by the appropriate expressions involving the continuous time matrices A, B, C, and D, and the sample period capital T. that's then just a direct substitution of those matrices and variable to generate the state space representation in the discrete equivalent matrices. Again, that's using this continuous time system described or parameterized by A, B, C, and D, those matrices. After this class, if you're now actually doing some of these discrete equivalents, you probably will let MATLAB do that for you, but now you understand what that represents. And for MATLAB, you can do it many different ways. You could do a zero order hold, and that's actually the default. If you didn't specify the method, if you just used two arguments, argument 1 and argument 2, in the C to D function, it would default as a zero order hold equivalent. You can also do the bilinear or the trapezoidal approach using the method designated as Tustin, or you could also do, for the single input, single output systems, the pole zero mapping that we've talked about, if in quotes, single quote, you put matched for the method. You can then quickly take a continuous time system, either in transform expression form or in state space form, together with the sample period. That's what capital T, capital S stands for in this functional description, and produce a discrete equivalent. Really, I think it's fairly straightforward to proceed with what you need to do stepwise relative to the previous discussion. You just have to keep track of, do they want scenario 1? Do they want scenario 2? And depending on what they want, how do you proceed? Suppose now somebody said, I want the zero order hold equivalent of the following system. G of S is now 1 over S plus 2, S plus 3. And now you might need to find the sample period, capital T, and you could do that by looking, if you weren't trying to speed this system up, you would look at the highest pole, or the fastest pole, which in this case corresponds to this pole at S equal to minus 3. That's the fastest pole. And then you would use omega sub S is 30, omega sub F, which in this case is then 90, and you set that equal to 2 pi over capital T to evaluate for your sample period, capital T. But if you're now wanting the zero order hold equivalent, this is scenario number 2. And in scenario number 2, then, we have capital G of Z. We're trying to find this transform expression. That's 1 minus Z to the minus 1, Z transform of G of S over S. Or we simply put another pole in the G of S at the origin, so that now we have 1 minus Z inverse, Z transform of 1 over S, S plus 2, S plus 3. We could now do a partial fraction expansion. We now have 3 terms in our partial fraction expansion inside the curly brackets on the Z transform. We could now find those from a table and do a table lookup after we found the A1 and the A2. And once you've now multiplied what's left after Z transforming by 1 minus Z inverse, if I did the math right, you should end up with 1/6 minus 1/2 z minus 1 over z minus e to the minus 2t. And here I have not yet incorporated the sample period, and then this is now 1/3 scaling z minus 1 over z minus e to the minus 3t. That's a zero order hold associated with the transform expression. Maybe somebody now says, you know what, I want a discrete equivalent. I have a bandpass filter that I want you to now implement digitally, where let's say this bandpass filter is 10s over s plus 1, s plus 10. And you now are asked to do a numerical integration strategy using the forward approach, and that now immediately tells you what substitution you need to make for each of these s values in your expression. If they said, I don't know, what is the sample period? Well, now again, you would say, oh, the sample period needs to be 30 times the fastest. And if we're not speeding this up, this is a bandpass filter. We're not trying to change the dynamic frequency of this system. Now omega sub f is associated with the pole at minus 10. Or we now know that t is equal to 2 pi over 300, which if we approximate if we approximate pi with a number a little bit smaller than pi, which is 3, then we're moving in the right direction for approximation. And we could now use a sample period of 0.02. The discrete equivalent using the forward strategy is accomplished by replacing everywhere we see the s with z minus 1 over capital T. And on the quiz, you may have to look at a particular expression. It may not be left in this form. In this case, you might say, oh, that denominator, I'm going to rewrite that. I'm going to factor out a 1 over t from each of those factors. And now that I have 1 over t and 1 over t downstairs, or 1 over t squared, my g of z is now 10, 1 over t. Upstairs I have the z minus 1. Downstairs I have a 1 over t squared, z minus 1 plus t, z minus 1 plus 10t. Again, remembering t was 0.02. One of these t's downstairs is canceled by that one, and we now have 10t upstairs, so that g of z is 10t z minus 1 over z minus 1 plus 0.02, or z minus 0.98, and z minus 1 plus 10t, which is plus 0.2, and the 10t is just 0.02. We now have found a zero order hold equivalent using the forward numerical integration strategy for a bandpass filter. And you could, if somebody now said, oh, and that maybe wasn't, let me call that what it should be. Here was C of S. Let's call that C of Z. This is now C of Z, not G of Z, and this now becomes C of Z. If somebody wanted the difference equation associated with that, let's say that this is now some output expression or output signal over an input signal. That's now this 0.2 z minus 1 over z minus 0.98 z minus 0.8. Before you maybe cross multiply, you might want to say, well, let me multiply that by z to the minus 2 so that I now have it in terms of z to the minus 1 operators, and now I will end up with a y of n being a function of y of n minus 1, y of n minus 2, and u of n, and or u of n minus 1 and u of n minus 2. I'll leave the rest of those examples to your study, but that should get you in the right direction or point you in the right direction for studying for unit number 4.